Hi, this video is for the lesson You Lose Some, comparing functions using key characteristics and average rates of change. So in this video, we are going to focus on comparing properties of quadratic functions represented in different ways, and we will compare functions that increase linearly, quadratically, and exponentially by analyzing their average rates of change. So let's dig in. Let's say I give you these two quadratic functions written in general form or standard form. So I'm asking you, which of these functions has the lowest minimum point? So we should know how to find some key characteristics given the general form. I could also use graphing technology to help me. But when, let me see here, it says the lowest point, so that probably means the vertex. And because it says lowest points, it's already telling me it's an absolute minimum. I can always tell that from my A values of my general form. Those are both positive, so that tells me both the graphs are going to open upward. So I do have a minimum for my vertex. I also know I need my vertex. And one thing when finding the vertex, what helps me find the vertex is the x-coordinate, or the axis of symmetry, is by taking the opposite of b over 2a, and then I can use that x value, substitute it into the function, determine the y value, and that gives me my x and y coordinate of my vertex. So let's say I want to do that for f of x. So I want to find what the vertex of f of x is. So I'm going to use x equals, I'm going to use my formula, the opposite of b. So b in this instance is a positive 2 over 2 times my a value, which is 1. And that would give me negative 2 over 2, which is negative 1. So I have found the x-coordinate of the vertex for that function. So now I need to evaluate f of x for f of negative 1. So when I substitute that in, I need to find negative 1 squared plus 2 times the negative 1, subtract 3. And all of that, when I calculate it, it becomes negative 4. So I know that the vertex of this function is at negative 1, negative 4. So now I need to do the same thing. Either I could do that by using the formula, what I just did, but for g of x, or maybe let's use graphing technology to find that. So here I graph both of my functions. This is f of x, and I can see the vertex, yes, is at negative 1, negative 4, which I am now confirming. And g of x, I can see that that vertex, and I'm going to record this for myself, is at 1, negative 32. So to answer the question, which function has the lowest minimum point, I can definitely see that g of x, that vertex has a lower y value, so it means that that has the lowest minimum point. And I can see that from the graph too, that it was actually went lower than the other graph. What if I'm asked the question below? It says which function has a greater value at x equals 8? So algebraically, I can do that by doing what I just did before, and it's now finding f of 8. So when x is 8, I can see that f of x produces 77 is my output. And when I do that for g of x, I can see them output 66. So I can tell right away that f of x produces a greater value at x equals 8. If you wanted to know how to do that graphically, I know that I want to know where these graphs, f of x and g of x, intersect the vertical line at x equals 8. And I can see that g of x intersects at 866. That means when x is 8, y is 66 for g of x. And for f of x, I can see that that is at 877. So it confirms what I just did. But I can also be asked to compare quadratic functions that are given two different representations. So before I gave you two equations, but what if I give you a table and a graph for these two quadratic functions and ask you which one has the greater maximum? So by looking at the table, I can see here that this appears to be the vertex, because when I move a half below that value and above that value, their y values are equal. So that means I see symmetry around that one point. And I can look at my graph and see that my vertex is here at x equals 1 1/4, and I can see my y value is greater than 3. So already this has a higher or greater maximum than g of x has a greater maximum than f of x. But what if I asked you to compare two quadratic functions, compare their average rates of change? So just a reminder that this is the formula for the average rate of change. But if you're looking at that going, it doesn't make much sense to me. This is the best way that I remember. Is it says the average rate of change of any function over an interval is just the slope of a linear function passing through the beginning and end points of the interval. So really, this formula here can just be thought of as the slope formula. So you're changing your y's over your change in your x's, or y2 minus y1 over x2 minus x1. This is just written in function form. So it's just saying what is the difference in your outputs over the difference in your inputs. So, but again, it's beginning and end points of that interval. You're going to take those x and y coordinates and use that formula. So when I ask you, compare these two functions or average rates of change for the interval 0, 2, that means when x is 0 and x is 2, what are my outputs? And I need to use all of those values to calculate this. So graphically, let's look at that. So from 0 to 2, I'm basically saying if I focus in for x is 0 to x is 2, I'm going to take the endpoints of each function and where they lie between those 2 points. I'm kind of drawing a line. I'm going to find the slope of that line. So it's like drawing a line through, let's pretend I could draw a straight line on my iPad. Here, and then this is just a horizontal line. And you might already see that this top parabola has a steeper line than the parabola down here between that starting and end point. But let's go ahead and verify that. So I want to grab my values, my x and y coordinates when x is 0 and x is 2 for each function. So 0, -3, 2, 5. So 0, -3, and 2, 5. And this was 0, -30, and 2, -30. And I'm going to use the formula. Remember, it's just like the slope formula. So if I do my change in my outputs over my change in my inputs, then f of x has an average rate of change of 4. And when I do the same for g of x, I get an average rate of change of 0. And if you notice, that makes sense because this line, and I could use my slope triangles, has a slope of 4, and this has a slope of 0 because it's a horizontal line. There was no change vertically between those two endpoints because they had the same y values. Okay, now what if I wanted to zero in for the interval 3, 4? So I'm going to change the color just so we can visually see what's happening there. So here is when x is 3 and x is 4. And if I drew a line between those two, let me change the color a little bit here. Here and here, the steepness looks pretty similar. This is why we really need the formula to really verify that. So I want to make sure that I'm going to grab my coordinates when x is 3 and x is 4 for each function, and I'm going to use the formula. And so when I do that, f of x has an average rate of change of 9, and g of x has an average rate of change of 10. So I can see that g of x actually has a greater rate of change for that particular interval. So this particular method can also be applied if you're asked to compare different types of functions. So if I give you h of x equals 2x, which is a linear function, j of x, which is equals 2 to the x, which is exponential, and k of x equals x squared, which is quadratic, and ask you to compare their average rates of change for different intervals, I'm going to use exactly the same idea of what I've just done. So the first interval says from -3 to 3. So graphically, again, reminding you that that means I'm looking from here, x is 3, all the way to -3 or +3. And I'm really thinking about this as if I'm drawing a line between the points. And what you might notice is that the line, the linear function, that's just the line itself, okay? Then if I look here at the exponential, then that line is here. And then when I get over here to the quadratic, oh no, we got another horizontal line between that interval. So I can probably already see which has the steeper slope or the average rate of change, but I can also do that mathematically and calculate. First, I need to grab my coordinates at each of those starting and end points of the interval. And then when I calculate, I can see that in fact, the linear function has an average rate of 2, which is greater than the other two functions for that particular interval. So if you wanted to check yourself, you can pause the video right now. And for these particular functions, try doing it for the interval 0, 4, and 3, 4. If you want, for those two, you can pause that there, or I can slide this up and zoom in a little bit so you can see maybe what those particular output values are. Or you can use a graphing calculator to help you do that as well. So if you pause it, try it, unpause it, I'll reveal the answers. I'll wait. And if you are unpausing it or you just want to go ahead and see what happens, I will reveal that for the interval 0, 4, the quadratic function has a greater average rate of change, but for the interval 3, 4, the exponential function has a greater rate of change. Something that you might notice is the average rate of change for the linear function over any interval is just 2, which also happens to just be the slope of that line. I wonder if that will always happen for linear functions. And as we continue to move to the right, which function do you think will always have the greatest average rate of change? That is just a little something for you to wonder about.